Swayam Prabha. Digital India. Educated India.
First, we will start with the design provisions for groove welds because they behave in a very simple fashion. They do not completely alter the geometry, or the stress flow remains very similar to what it was in the parent material, and therefore the designing of groove welds is very simple. If it's a full penetration groove weld, we basically take the thickness of the thinner plate that is joined at that location. If it is a partial joint penetration type of a groove weld, then we take the effective throat thickness as we have discussed in the earlier sections, which is again basically can be taken as the summation of the two portions of the weld which are provided. So if the groove weld is subjected to tensile or compressive stresses, then the strength of such a weld is governed by the yield stress of the material. So which yield stress would we take? We take the yield stress of whichever one is the smaller of the weld and the parent material. So if we are using an Fe 410 steel, it has a yield stress of 250 MPa, and let's say we are using a EX40 type of a welding material, that is electrode, which has a yield stress of 330 MPa approximately, then we would use an Fy of 250 MPa. Okay, Lw basically represents the length of the weld. So let me draw it for an easy understanding. If we wish to join these two plates using a groove weld, let's say these two plates, and we provide a welded joint between these two plates, the thickness, that is the throat thickness of the weld, is this one that we will use in Te. In the third dimension, in the direction perpendicular to this plane, we will take the L value, that is Lw, that is length of the weld. So if it's a single continuous weld, we will take the entire length. If it is an intermittent weld, we will take the length appropriately. F multiplied by Fy. So basically, Te multiplied by Lw gives us the total cross section which is subjected to tension, and this plate is subjected to tension in this direction. So the entire cross section which is subjected to tension, that cross section is given by Lw multiplied by Te. This will be multiplied with Fy. Fy is the yield strength, minimum of the two, because the parent material and the weld material, they are acting in series, and therefore the overall strength will be minimum of the two. That's why Fy is taken as the minimum of the parent material and the welding material. And then we divide it with gamma mw, where gamma mw is basically partial safety factor for welded joints. There are two different values given for partial safety factor for welded joints in the Indian code. It is 1.25 if it is a shop weld, and it is 1.5 if it's a field weld. The reason for providing a larger value for a field weld is that in field, typically there is a high likelihood of making some kind of a mistake and allowing some kind of impurities or some kind of a sharp surfaces or not fully fused surfaces into the weld. So because field welds are relatively less reliable, therefore the factor of safety is increased, so the design strength is decreased. When we design the same weld for shear, again through an example, let me show you. So these are the two plates that are joined together using a groove weld. Then it is subjected to shear force like this. If this is the shear force demand, again the cross section area that is going to resist the shear force is the same, which is Lw multiplied by Te, like before, that will be used. And instead of Fy, this time we will use Fy divided by root 3. And we might have discussed where does this root 3 come from? This root 3 comes from the von Mises failure criteria for ductile materials. So for ductile materials, when they are subjected to pure shear, they yield at a shear stress of Fy divided by root 3, if Fy is the yield stress in pure tension, divided by gamma mw. Gamma mw again is a factor of safety as discussed before. So this is how we calculate the shear strength of a groove weld. Here is an example. If we join these two plates, one is of 16 millimeter thickness and the other one is a 14 millimeter thick plate. So this one is 14 millimeters, this is 16 millimeters, these are joined, and we are using a full penetration weld, which is basically the entire thickness of T1 is welded with T2, and a factor load of 430 kilonewton is to be applied in tension. So these are pulled in tension. Length of the weld is given as 175 millimeter. When we say length, we mean the value, the dimension in the direction perpendicular to the screen. So in this direction, the length is 175 millimeter. Okay, it is mentioned that it is a shop welding weld, therefore gamma mw value will be 1.25, and we need to check whether this weld is able to resist this much of load or not. So we know that T1 and T2, between T1 and T2, T1 is smaller, which is basically equal to 14 millimeters. So if this is 14 millimeters, so Te will be 14 millimeters. Lw is 175. Fy, which is minimum of the two, and I have not mentioned the weld material, but weld material has 330 as we discussed before, and when we compare that to 410 Fe410 yield stress, it turns out to be 250, which is smaller of the two, so we will use 250 as the yield stress, 175 as Lw value. Te is the size of the throat thickness divided by gamma mw, and what we get is the design capacity of this weld, which is 490 kilonewton, and the capacity is greater than the demand. The demand was 430 kilonewton, therefore this welded connection is found to be safe. Now let us take an example of a groove weld which is not subjected to tension, but it is subjected to bending. Now as we know, bending is basically consists of compression and tension combined. So here you can see a plate which is joined to this plate. Both plates have the same thickness. The thickness is given as 18 millimeters. Okay, this is again a full penetration weld, that means the entire thickness of the plate is welded together. The moment demand is given as 19.5 kilonewton meter. So if I may show it this way, the moment is actually acting in this direction. Sorry. And in this direction here. So these are the moment directions. The plate has in the other direction, this is the plate thickness. And this is the thickness of the weld, what you can see here. So now I hope you can visualize this, how the moment is applied, in which direction the moment is applied. So as a consequence of this moment, we can expect this portion of the weld to be in compression, and the bottom portion of this weld or the bottom portion of this plate to be in tension, and the neutral axis can be assumed to be at the center because it's a symmetric cross section. So first we will start with calculation of stresses, and we will see whether the stress here is within the permissible limit. That is the basic design philosophy. So in order for us to calculate the stress, we need to calculate the moment of inertia of the plate, which is basically the same as the moment of inertia of the weld. So we are basically going to calculate the moment of inertia of this cross section. right? Which is also the same cross section, that is the weld. So we will calculate the moment of inertia of this cross section. This cross section moment of inertia will be bh cube divided by 12, where b is basically the width, which is equal to, I'm sorry, the bh cube divided by 12, wherein the h will be this and b will be the thickness. So this is b and this is the h value, right? So half of the h is above the neutral axis, half of the h is below the neutral axis. So h will be 180 millimeters. The thickness is given as 18 millimeters. So we will use 18, 180 cube divided by 12. This gives me a moment of inertia of 8748 into 10 to the power 3 millimeter to the power 4. Now we can very easily calculate the maximum stress in such a plate. If we know the moment of inertia, the maximum stress sigma will be my divided by I. The same sigma will be present in compression at this edge, and it will be present in tension at this edge. So this is sigma tension, this is sigma compression, but the same value, right? We do that, we put the value of the moment which is applied, kilonewton meter, and then y value will be the distance from the centroid. So in this case 180 divided by 2, that is 90, divided by the moment of inertia which we had calculated before, and what we get is the stress value, which is 200.62 Newton per millimeter square. How much stress is this weld allowed to take as per the limit state of design? The weld strength can be calculated as, which is basically Fy, which is minimum of the two yield stresses, Fy of steel and Fy of the electrode. So we use that, we get 250 MPa as Fy. We substitute that divided by 1.5, because this is a field weld. If it's a field weld, the factor of safety will be 1.5. We use that, and we can get the strength, weld strength, which turns out to be 166 kilonewton per millimeter square, and the demand or the stress was 200 Newton per millimeter square. And as a result, we can say that this weld is unsafe because the demand is greater than the capacity.